So we've seen that we can directly transmit our digital signal in the baseband case, but not for the broadband case. So there's something called modulation needed. So, well, if we talk about signals, this is all our electromagnetic signals, and they travel along a wire or through space. And the simple solution baseband, we take it as it is, our signal, and send it over the medium, copper wire, for example. So that was our cable codes, line codes. But for the second solution, we have to do something. We have to modify a so-called carrier. That's our carrier analog signal. And this modification of a carrier depending on a digital signal, in the end our data, that's called modulation. And we can do this in many different ways. So let's have a closer look into a signal again. So in this case, a sine wave. And this sine wave has a certain amplitude. So certain amplitude A shown here, that gives you, well, how strong the signal is, a certain frequency. So that's frequency or duration of one oscillation, one period. And we already learned something about the phase. And modulation now means we shape the carrier frequency, we shape the sine wave based on our baseband signal, which represents our data. So we have our signal, and this baseband signal as it is can now be used to modulate the carrier. So we have two steps of modulation as we learn. We have a digital and we have this analog modulation. And in the end, I will go through the steps, and in the end, we have a modulated signal. Here shown a very simple way of modulating. So you see basically our baseband signal is still, you see, reflected here. You see this? In this case, modulating the amplitude here, the strength here of our carrier frequency. This is why it's called amplitude modulation. So in this case, we modify here the amplitude. And the device doing so, it's called a modem, so it's a modulator, demodulator. Okay, coming back. Remember, that's a very general. This also works for analog signals, but we have digital signals. So what are the typical steps? So we have digital signals. We learned we represent our ones and our zeros. Here, in this very simple case, we see the 1 is, for example, a certain value and 0 is a certain value. So we take this digital signal and now we modulate our analog carrier. In the first example, we manipulate the amplitude. And because we do this with digital signals, this is also called shift keying. So it's a discrete modulation of the frequencies. Modulation analog works also with analog signals, so amplitude modulation and frequency modulation, for example, works perfectly well also in an analog way, and this is the classical AM/FM radio. But here we have digital signals now manipulating the carrier. So we have discrete signals or digital signals, and they, for example, say, okay, we do not touch the carrier, for example, that's shown here, and then we manipulate the amplitude, make the signal weaker, for example. So that's very easy to realize. So 1 is the strong, 0 is the carrier, but with a lower amplitude. Very easy to realize, don't need much bandwidth, but as you can imagine, what happens if you have attenuation here in the signal caused by whatever, then we interpret this also as a 0 because the signal is weak. So this is not really weak. So simple amplitude shift keying is not a good idea, it's not very robust. But is this always true? Well, think of optical transmission. This is the extreme case where we simply say light on, light off. We can do this amplitude shift keying, light on, light off, in the extreme way in fiber optics. So a 0 can mean no light at all, and a 1 is bright light, because we have ultra low interference in fibers. So there is not that much noise from the outside. So we can manipulate, that's one way of doing the amplitude. We can also do something with the frequency part here. So we can change the frequency. Also again in a discrete way, and this is why it's called frequency shift keying, FSK. So you see, for the 0 in this example we take a higher frequency, and for the 1 we take a lower frequency. So we take two frequencies. If we show this in the frequency domain, we code in this example the 0 as a higher frequency and the 1 as a lower frequency. This requires more bandwidth, because we learned, okay, depending on how we do this, that's our bandwidth we need. This wastes frequency, needs a lot of bandwidth, but that's the initial principle used in data transmission over the phone lines. So maybe if you watch these old movies, you hear these certain sounds of beeping at different levels, and this beeping actually encodes the bits. So you had different, frequencies for sending zeros and sending ones, and also for the received zeros and received ones. And this allows you to transmit bits in both directions, so full duplex at the same time, both directions, using the classical old telephone system where we know, okay, we can use everything between 300 and 3400 Hertz. And then we simply define, okay, where is the 0 and the 1 in one direction, and where is the 0 and the 1 in the other direction. So we have 4 different tones, and we can transmit whatever we want. So that's the basic idea. This sounds strange. So we use these 4 tones and we code our bits. But we will see an example what is done today at DSL. So our DSL modems, it's pretty similar. So that's the initial principle on this old modem technology. There's a third component of our sine wave we can use, and that's the phase. The phase, basically, you remember, that means we shift a signal. So we have a nice sine wave here, for example, should be a sine wave, and then we can shift, for example, and say, okay, we shift the sine wave in a way that, for example, the dashed sine wave is now shifted by a certain phase, and this, in this case, we shift by 180 degrees or pi. So that's the phase shift here. That's the idea. And if we then concatenate these parts of our carrier, we see here the phase shift, and so we basically code the bit values in the phase shift. And there are different ways of doing this. We as humans cannot hear phase shifts in acoustic waves, but the demodulator can do this. It's quite robust because interference will not simply create a phase shift. So it's quite robust against disturbance. So, and it's a very, very generic solution. And we can combine this in many different ways. So in an overlook, you see we have a certain binary signal. So this is fine for baseband, as we learned. Okay, this would be a classical non-return to zero code. We saw we can do it better ways, 4B, 5B, etc. But if we have to go broadband, we have to modulate this. And for fiber optics, this would be a very simple way of doing it: light on and light off. And we can do this with frequencies. That's what used on the classical phone modems, different frequencies for ones and for zeros, also for different direction. And then we can do this in a bit better way, coding here in phase changes. This requires a bit more elaborated receivers. And then we can do even more. We can combine all these things. So we can go ahead and do not say, okay, we have two phases, like a phase shift of 180 degrees, 0 and 180, but we can do more. So, and then we come to schemes like QPSK, where we have 4 phases with 4 different states, and this doubles the data rate. Why? Now suddenly we represent this in a way of, what we've seen here is a so-called constellation diagram, where you say, okay, we have a point in the constellation diagram, and this point now codes 2 bits, 1, 1. Why? Because we have the same amplitude. Amplitude is the length of this vector. Basically, that's the circle here around. So all those 4 points, they have the same amplitude. But now we code the bits in phase shift of our signals. So that means if we want to transmit 1, 1, and after this 0, 1, we have a wave of a certain frequency depending on the medium, and code now a phase shift of pi half or 90 degrees, for example. So that's the idea. And so this can be well described with the help of these so-called constellation diagrams. Without going into further details here, this is something quite common, especially in wireless communication. So we see now in this way of describing this vector, the vector has a certain angle, and a phase shift is actually, we let the vector rotate here in this plane. So in the end, we see this is sine wave, and we can code our bits now certain points of the sine wave, and then we concatenate these fractions of our wave. In real systems, we have much higher frequencies, so this is just to show this. So it's much higher frequencies, and then suddenly we have this shift, and we code here our bits basically in these jumps in the phase. So that's the core idea. So not only 2, so a phase shift of 180 degrees, but here we can have 0 degree. So if we have no phase shift, in this example would say, okay, we send 1, 1 and 1, 1 and 1, 1 and 1, 1, so there's no phase shift. But as soon as we then send 0, 0, we have a phase shift of pi or 180 degrees, etc. If we then send again 1, 1, we have again a phase shift of pi. So that's the idea of coding our bits into phase shifts. And as we see here, because we have 4 points in a constellation diagram, we can code 2 bits at one time. So now, well, we can do many things. Okay, why not having more and more and more and more points? So a very simple scheme is the binary phase shift keying. Again, constellation diagram, we have a point here. So we can say this is a 0 and this is a 1. And if we transmit 1, 0, we have a phase shift of this pi, 180 degrees, for example. We can do the QPSK as shown here. We can do many more things that, for example, phase shifting only if 1 is the next bit, and for 0 we have no changes, so differential binary phase shift keying. So that's something that can be done. And you see, you modulate your carrier frequency. And here you see how we encode phase shift, okay, ones following ones, and for zeros there's nothing. We just go through. So that's one way to where there are many different PSK versions. Plus we can now combine PSK, so the phase shift keying, with amplitude modulation. Whoa, this leads to a very basic scheme called quadrature amplitude modulation. So we have 2 amplitudes, So that's amplitude 1, and that's amplitude 2. So we have stronger and weaker signals, and we can now combine this coding. You see now 8 points in the constellation diagram. So if we have 8 points, we can transfer 3 bits per symbol. So that's the idea. So you have basically now a scheme that really scales well by inserting more and more points in the constellation diagram. And you see that this is also reflected then in these snippets of the carrier. In reality, again, there are many more, but shown here just part of it. And if you now combine this, if you transmit 1, 0, 1, and after this you transmit 1, 1, 1, that means you jump from 1, 0, 1 to 1, 1, 1, which is a phase shift of pi, or 180 degrees, no matter clockwise or counterclockwise, plus you change the amplitude from the A2 to the A1. And this is reflected here. You see, okay, now we have this stronger carrier. So that's the idea here. So you combine now, in our simplified example, this, and then you jump and you have a stronger signal. And the receiver demodulator is able to detect the different amplitudes plus the phase shift. But remember, amplitudes, they're a bit error prone due to interference, but in this combination it can be used. So you can do now more and more and more depending on the coding. We can have 16 symbols, or here 64. And this goes up to 1024, 2048, 4096, etc. But where's the limit here? The problem here again is noise. What happens? So if you receive, look at the first example here, if you receive something, for example, let's say this here should be the 0, 0, then you transmit 0, 0, there will be noise, and noise, let's say on the receiver side, receive something here. Maybe a stronger, maybe a weaker signal. Remember, the length of the vector is the strength, the amplitude. So you receive something here, but still it's in the upper right-hand corner. So you say, okay, everything here in this corner is 0, 0. Perfect. And then maybe you receive something here, and this could be then the 1, 1. And as long as it's in the lower left-hand corner, then it's a 1, 1. Perfect. But now what happens if you code more bits here per symbol, 4 bits per symbol? Now, if you receive something around this, do you map this to this point or to that point? Or even worse, if you receive something here, assuming the same noise, what does it mean? Yes, it's still in the lower left corner here, but how to map this to the correct symbol if you code now 6 bits per symbol? So noise again limits. Remember, we had these multi-level symbols, and now we have multiple points in these constellation diagrams, and we cannot simply go to even higher and higher and higher modulation schemes if we have noise. And today's systems, they automatically adapt the modulation scheme. So if there's more noise, you switch over to even simpler systems. And if you have extreme noise, we go to the binary phase shift keying scheme. Has only 2 points. And typically you always be able to receive this. So this is quite common, for example, for satellite systems. So satellite, weak signals, a lot of noise, then this is very robust. QPSK is also fine. And you see, especially in wireless systems, but also wired systems in modern technology, that today's systems, they can adapt automatically depending on the noise level. Noise, well, you check how many errors you have in your signals. How you check for errors, we will learn on layer 2, next chapter. But if you know, oh, there's an error, then let's try a simpler modulation scheme. If everything is error-free, why not going to one of these schemes where you can see, okay, this is fine. So maybe we can transmit now 6 bits, 8 bits per symbol. That's the idea. Okay, so some questions. So why using broadband? Why not using baseband? That's fine. So we have a wire and we simply transmit our baseband signals. Why and when do we have to go to broadband signals, and how do we create them? Then remember, what is modulation and why is it called shift keying, and how do we achieve it? There are different ways of doing this. Then a simple question, can baseband signals carry more bits per second or broadband signals? So this depends on what? So is baseband better or broadband, or can we say this at all? So we go, now the trend is clearly to more bits per symbols, yeah, even higher data rates. But what is the major problem if we do so?